Well, good morning or good afternoon or good evening, everybody. My name is Doug Finke. I'm with the Quantum Computing Report, and we have two great panelists here who can talk about quantum cryptography and communications. And I think you'll find it a very interesting session. We will be taking questions, so I would encourage you to enter any questions you have in the chat, and we'll try to answer them if we can. But I'll start and have each panelist introduce themselves, and we'll start with Dustin Moody, who's from the U.S. National Institute of Standards and Technology. And Dustin, maybe you could say a few words about yourself and what you're working on.
Sure, thanks, Doug. So like he said, I work at NIST. At NIST, there's many things that we do there, a lot of very interesting, cool science things, but where I'm involved is we do standards for cryptography for the federal government, which we know that those get picked up by industry and other organizations around the world. And my background is in mathematics. I have a PhD there and I do research, but right now the main project that I'm focusing on at NIST is what's called our post-quantum cryptography standardization project. So that's a project that's been going for a few years. The thread is, of course, that if there's a large-scale quantum computer, it would be able to break some of the crypto systems that we use today. Namely, it would break public key crypto systems like RSA and elliptic curve crypto. And so as a result, we need to have new crypto systems that would be safe or protected from attacks from a quantum computer to replace these algorithms that would be broken. So people around the world have been aware of this threat for a while. And about 5 years ago, NIST launched a large international competition-like process to kind of vet and evaluate new crypto systems. So experts from around the world have designed some new crypto systems that are believed to be quantum resistant and sent them into us where we're running kind of a competition to find the best ones. And that has proceeded through a series of rounds. Initially, we had about 70 of them that were sent in. And after the first round, we whittled it down to 26. And right now we're in the third round and we have 7 finalists and 8 alternate candidates that are still being evaluated. Roughly probably about the end of this year, beginning of next year, we will announce the algorithms that will be selected for standardization so that we can begin our transition to post-quantum cryptographic systems for public key cryptography. So that's a little bit what I'm involved with and this project I'm working on and what we'll be talking about a little bit.
Okay, great. Thanks for the introduction. And we'll turn it now to Denis Mandich. Denis is with a company called Qrypt. He's actually speaking from the Freedom Tower in New York City, and you can see the Hudson River in the background there, so enviable offices there. So Denis, why don't you tell us a little bit about your company and what you're working on?
Sure. My name is Denis Mandich. I'm the CTO here. I'm a physicist by background, string theorist. I spent a couple decades in the US government working on some of these quantum secure systems. And today at Qrypt, we're implementing some of the NIST finalists that Dustin is working on to bring some of the software that people use today into this post-quantum crypto era. We also build fully quantum secure systems that are not just quantum safe or quantum resistant, but they're actually impervious to any type of attack. These implement one-time pad-based systems as well for really ultra secure applications. These are in 2 types of technologies: the common IP-based systems that run the internet, and then the operational technologies that you'll see for critical infrastructure as well. One of the fundamental pieces that we need for that is the ability to generate large amounts of random numbers through quantum entropy sources.
Okay, well, very good, Denis. So, one thing I should mention, I actually did a study of this once. Over the next 10 to 20 years, the world's going to have to either upgrade or replace tens of billions of devices to a new type of cryptography because of quantum computing. And for those of you who may remember the Y2K effort 20 years ago, sometimes they call it Y2Q, years to quantum. So there's going to be a big effort over the next 20 years to do that. But let me start asking you a question first, Denis. Is that Dustin? You mentioned that you'll be coming out with your selection of your standards, let's say, within the next year or so. If I'm in an enterprise right now, and I'm a little bit concerned about that, is there anything I should do right now to prepare for this upgrade, or should I just wait until you guys finalize on your standard?
It's a good question. There are some things that you can do now, and there are some things that you probably should hold off on doing. You don't want to rush out and take any, you don't want to rush out and start implementing a crypto system before it's been standardized. I would recommend that you wait until there are standard algorithms that specifications have been out there for. But what you can do is start getting some information. NIST has an organization called the NCCOE, the National Cybersecurity Center of Excellence, that's leading a project to help organizations with the migration to post-quantum cryptography. And they've written a white paper and have several resources on their website. So if you search for NCCOE and post-quantum crypto, you'll find their project that has a lot of information about getting ready. I'd also recommend that you start building an inventory of your crypto and the different implementations you have that are deployed that use crypto, and looking at what type of crypto is it? Is it public key crypto that's vulnerable? Is it in a place where you can easily swap out a new algorithm? We often refer to that as crypto agility. You can start learning about the candidates that we have as finalists, and you can test them out, prototype them, see if they're going to fit for your different needs, your use cases, your applications, see if there's any issues that might arise. Some of these new post-quantum schemes have larger key sizes, so you want to explore that in advance, if that would be a problem. But mainly you'd want to just ensure that as you start planning, knowing that a transition is coming up, that you are ensuring crypto agility and support for new algorithms, because you're going to have this transition coming up, and make sure that your organization is aware of the quantum threat and you're taking steps so that you'll be ready for it.
Okay, great. Denis, you want to add anything to that?
Yeah, I think just the earlier that you start experimenting and prototyping, the better, because as Dustin mentioned, simple issues like massively larger key sizes in some of the algorithms will affect performance and infrastructure. You may not have the systems today that will support it. You should have an idea of what that will look like in the future, because it's not a light switch. It's not like we will transition to PQC one day. That happens 2 years from now. It'll be a phased process the way it was the existing systems that we use today.
Okay, great. So I have a follow-up question on sort of your process, your whole stuff that you're working on, Dustin. I've heard you mention in the past that in your selection process, you're actually going to select like multiple, maybe 2 or 3 types of algorithms for like each type of encryption or each type of use case. Could you sort of explain, why you're going to go for multiple algorithms? Maybe it's only a couple, 2 or 3, but why you're doing that instead of just one?
Yeah, so NIST has done some of these crypto competitions in the past. Long time ago, we did AES, and more recently we did the SHA-3 competition, and each of those did have one algorithm that was selected and standardized. This post-quantum crypto standardization project will be different, like you noted. We expect to have a few different algorithms, and let me explain why. First, there's 2 different public key crypto systems, crypto functionalities that we have standardized in regards to public key crypto. First is public key encryption or public key establishment, and then a second are digital signatures. So there's 2 different functionalities that we're looking for, and we need to have different algorithms for each one of them. Now, for each one of them, we expect to have more than one as well. So for encryption, a lot of these algorithms that are being looked at, this is still a fairly active research field, and we've been vetting them for a number of years, but we don't want to put all of our security eggs in one basket. Some of the most promising ones that we're looking at are based on what are called lattices. Well, it could be some, research breakthrough comes out in a few years that has some new unexpected attack and would mean that we would need to switch to something else. We want to have more than one crypto system standardized in case that happens. Another reason is that some of these post-quantum systems, their performance profile is a little bit higher than we're used to right now. They have larger keys. Some of them have different efficiency things, like maybe their key generation time is a little bit longer. Some of them have very large public keys, but small ciphertexts. Some of them have small public keys, but large signatures. So depending on your use case, maybe one of these algorithms would be better suited for what you're looking for. Maybe you need a really small signature. Well, there's a post-quantum algorithm that has that. But another use case might need a small public key, or maybe just a balanced public key and signature size. So both for performance reasons and for security reasons, we will standardize probably 2 or 3 algorithms for encryption as well as for digital signatures.
Okay, great. And let me ask you a question, Dennis. We've been talking so far about post-quantum cryptography, PQC, but there's actually 2 different approaches that people are talking about to develop quantum-resistant cryptography. There's the PQC, which is essentially a math and software-based approach, but there's also QKD, which stands for quantum key distribution, which uses quantum physics. And Dennis, maybe you could explain perhaps your views in terms of where each of those techniques might be applicable, more applicable than the other.
Sure, and full disclosure, I'm a physicist, so in physics we trust. QKD is a great solution that actually has 2 modes of operation. One is that we can distribute AES keys, effectively reach the level of quantum resistance or quantum safety with it, or they're robust enough today to actually distribute one-time pads, and if they're used for that, they're actually quantum secure. PQC and QKD have different use cases. QKD is now distance limited in a trusted node network model, where you have a single unbroken piece of fiber connecting 2 endpoints where you can simultaneously generate all the key material that you need. So that's great for maybe critical infrastructure, for places where the military or the government might own the right of ways and the actual fiber that is used for these communications channels. But it's not good for communicating between Europe and the United States for banking or something like that right now, because we don't have quantum memory, we don't have quantum repeaters. But there's plenty of places between data centers that it could be used today and bring a different level of security with a different framework around it than PQC, which is more like the Swiss Army knife for all the applications that we use today, messaging, file transfer, and so on.
Okay, thanks. Dustin, I'll let you add to that. I know you spent the past several years just working on PQC. Just interested in your thoughts on QKD, whether there's any applicability with that.
Yeah, I agree with what Dennis said. They have different use cases. It's kind of interesting that post-quantum is the result because quantum computers will break crypto systems, whereas QKD is the idea that you can use these quantum technologies to create crypto systems. So they kind of have a different foundation. One's more on math, one's more on physics. But like Dennis said, the use case for a QKD is probably more for more high-end, secure, government, military, that kind of thing. Whereas PQC will likely be used more for what we traditionally use, a lot of communications protocols online to transmit information. And it doesn't have the scaling challenges that QKD has. So there are use cases for both. I think PQC will be more widely deployed worldwide for more applications, but both are important technologies.
Okay, great. It's good to hear that you guys are pretty much in sync. One of the things that Dustin mentioned was the fact that there are differences, and when people want to start implementing this stuff, things like key sizes will be different. And Dennis, maybe you could talk a little bit. I know you've expressed to me privately your concerns about the safety of keys, key generation, and the fact that you have longer keys now in post-quantum cryptography. maybe you talk a little bit about some of your concerns and things that people should do to perhaps come up with a more robust set of keys.
Yeah, the issue with most key generation mechanisms that we use today, they're based on electronic noise, which has no fundamental proof of randomness. Only a quantum measurement can give you a true random 0-1, where it's not because I don't have information about the system. I wasn't able to engineer enough around it. It's because fundamentally it can't be done. And we've seen this, from the beginning of cryptography, that the easiest way to attack a crypto system is not to try to break the crypto mathematically with supercomputers. It's we'll attack your entropy source, the thing that generates your keys, and then make that non-random or highly biased. And then I can just guess what your keys are and decrypt everything. And this happens with increasing regularity, either deliberately or inadvertently. Crypto AG is a famous one that the CIA ran. I like a recent one that the Russians ran. It's called Reductor, where the pseudo-random number generator in browsers was compromised to be non-random, and then they could just decrypt everything in real time. But it's happened accidentally as well, where we look at the certificates that are out in the wild today. Key Factor did a study on them recently and found that 1 in every 172 of them share a common factor. So it's a persistent problem. Whenever people look at it, they find that there's a lot of non-random behavior in the systems that generate the key material that we need to secure our crypto system. So we build quantum random number generators with the national labs around the world to overcome that problem, make it available at scale, and make it deployable through the cloud to make it easy to use for these much larger key sizes that you find in PQC.
Okay. So if you've been following the random number generator, articles of various types, there's actually a couple different types. Some people talk about certified quantum random number generators, and other people talk about random number, just standard quantum random number generators. Maybe you could describe the difference and where you might want to use one or the other.
Yeah, so there's no industry standard for what does it mean to be certified, because until NIST issues a new standard for it and there's a FIPS compliance requirement, there's really no certification authority in the traditional sense. What people mean is, for example, if you use a quantum computer to run a random quantum circuit, then the output of that circuit theoretically could be certified, but that's not a well-defined term. And using a quantum computer to generate a random number is like a Rube Goldberg machine for something that we do with simple electronics. Just doesn't make sense when we need gigabits per second, a random number generator output for crypto systems, and a quantum computer will take 2 minutes to put out a couple hundred bits. So it's really an emerging process. We're involved with the ITUT in Geneva on that certification process, and what is the standard for global financial network infrastructure for QRNGs. That's just coming online today, and we'll see authorities from the gaming industry and everywhere else come up with a new standard that we'll call certified.
Okay, yeah, it is important because I can go out today and buy on Amazon a random number generator for $50. And the only problem is I don't really know what's inside the box. And, there could be someone who had messed with it and it wasn't quite as random as I thought. So you do have to be careful.
Been done before.
Yeah. Now, Dustin, I have a sort of another question, which is there's also talk about hybrid post-quantum cryptography, where you sort of combine the PQC algorithms that you're working on, as well as classical encoding like RSA. Maybe you talk a little bit about that and whether or not you recommend that people look at that at all.
Yeah, so there's certainly been a lot of interest in hybrid systems where you're combining a post-quantum algorithm and a classical algorithm. We've talked to a lot of industry partners, and they seem to think that that's a good way to transition into post-quantum algorithms. Maybe we're not quite sure, because it's still a research field, we want to ease into it a little bit. when we do this. And so by combining both, the only way someone can break that hybrid scheme is if they can break both algorithms. So you're ensuring you've got quantum resistance, and then you still have the traditional cryptography that we're relying on. To us at NIST, that makes sense as a way to transition into post-quantum schemes. We don't think that'll be a long-term solution, but in the first few years, that certainly might be a good idea. We updated one of our standards, SP 856C, to allow you to do that for key establishment in a way that you can still get FIPS validation. So the FIPS validation would only be speaking to the classical crypto system that's currently NIST approved. We don't yet have a post-quantum one approved, but we describe a way where basically you can concatenate the shared secret from a classical algorithm like RSA and a shared secret from your favorite post-quantum algorithm, and then you'll run that through a key derivation function, essentially making a hybrid scheme, and it can be FIPS validated. Not everyone agrees with that. Recently, the NSA gave a talk at a workshop I was at, and they don't see hybrid as a good solution for them. So they plan on transitioning straight to post-quantum algorithms when they make their transition.
Okay, very good. So let me just take a quick side step. We'll get back to cryptography, but you know, cybersecurity has been in the news quite a bit lately. And since you guys are sort of at least involved in the periphery, besides the encryption aspect of it, are there other aspects that you are personally concerned about with regard to cybersecurity that you know you would recommend end users pay attention to? And I'll start with you, Denis.
Yeah, we are close with some AI machine learning companies. And one of the issues that when looking for errors in whether it's random number generation or the software implementation of algorithms, looking for those flaws was largely a manual process before with regular computers. When you start combining the next generation of AI and machine learning with quantum computers to discover those flaws, they're probably far more ubiquitous than we know today. And that's a little bit scary because a lot of this data, you know, we always talk about it's been harvested now, it'll be decrypted later. You might not have to decrypt it. You may just be able to unpack it some other way with these new tools that we're seeing come online. So I think the cybersecurity landscape is going to get a lot harder for a lot of companies. We're going to see a lot of these older technologies have critical flaws that have been implemented for years that we don't discover for 2 or 3 years.
Okay, Dustin, or anything in specific that you're concerned about?
Maybe I just add that we've learned that crypto transitions take a long time, and there's lots of unexpected problems that you encounter on the way. So as we start to transition, there's going to be things that we didn't think about. Something might not fit when we hoped it would. And like Denis said earlier, people aren't usually breaking the crypto algorithms. They're usually finding some vulnerability in the implementation. So I'm more worried about those sorts of issues rather than someone breaking the actual crypto system, but just making sure that the transition goes as smooth as possible. And for that, it takes a lot of people planning ahead. And we have a lot of people working on that, but we need more of that to go on so that everything will work out.
Okay. So we're getting some questions from the audience, so let me turn to those right now. And the first one's really for you, Dustin. There's some discussion about what we'll call a round 4 of the NIST competition. Maybe you could talk a little bit about that and what you're looking to do right now with that.
Okay, so we have finalists and we have alternate algorithms that we're evaluating. The finalists are the algorithms that we think at the end of the 3rd round would be ready for potential standardization if we select them, and that they would fit most use cases. They'd be good all-around algorithms. We also have some more alternate algorithms that we think need a little bit more time. So when we announce the first algorithms that we standardize, we also expect to name some of the alternates that we will continue to study in a 4th round of evaluation. And that way we will continue to have cryptographic diversity, where if we're relying on lattices for our main algorithm, some of these alternates are based on codes or are based on isogenies of elliptic curves. So we're continuing to look for those alternate candidates to see if they will be ready for standardization. They just need a little bit more time.
Okay, very good. And so there's another question. You guys, have been doing this for many years. Various types of algorithms you've been standardized. And have you given any thoughts to, after you complete this, post PQC program, whether or not you would, what your next project will be, whether it will be QKD or anything else?
Good question. I think the post-quantum thing is going to go on for a number of years, even after we get these first standards. Like I just said, we have a fourth round, and this is a pretty active field of research. So I think we'll be continually vetting new algorithms and seeing if we need to revise our standard because something better comes along, or if there's any attacks that show up that we need to adjust anything. There are other areas that are very interesting. NIST has projects involved with lightweight crypto, threshold crypto. We keep up with active research areas like fully homomorphic encryption. That's a very exciting area, and there have been some industry standardization starting to happen a little bit. And that's something I think could be very interesting for NIST to be more involved in as well.
Okay. Are there any possibilities or any thoughts given to NIST getting involved with standardizing QKD protocols?
Yeah, so our group doesn't do as much with QKD. We're more math and computer science. There are some physicists at NIST who are involved with QKD standardization efforts. In particular, there's one of my colleagues, Alan Mink, who's involved with some of those efforts. I don't know as much about that. I think NIST isn't putting as much resources right now into that. That could change in the future. Maybe Denis has more information on what he knows.
Yeah, we're involved in 2 projects with QKD. One is obviously for quantum internet, where instead of transmitting digital data, we transmit qubits. Another one is with a government lab level QKD technology that we may combine with some of the crypto systems that we're using today in a hybrid environment. So you can use both in the different applications that are available to you.
Okay.
I don't think it'll be standardized, but that's just my personal
Yeah, I think there are some other groups that are looking at it, either IEEE or one of the groups, but I can't remember which one's looking at it offhand.
I think ETSI, they're a European standards organization. They have some efforts as well.
Okay. So another question came in from the audience about the use cases for PQC, and maybe again, Dustin, you could talk about passing keys as one use case, and then digital signatures as another one. Maybe just explain that a little bit more for some of the folks in the audience.
Sure. So public key cryptography, traditionally it gets used in the 2 functionalities that Doug was just mentioning. It can do encryption, but typically the way we see it done today is you will use public key encryption to create a shared key with whoever it is that you are communicating with. Maybe you're emailing a bank or going to a website and you've never established a shared key with the other party because you're 2 different people online. Well, you'll use public key cryptography to create a shared key in a way that nobody else could figure out what it is. And then once you have that shared key, you typically switch over to a symmetric key crypto system, such as the block cipher AES, which is a lot faster to encrypt your data with. So that's one of the uses, is for key establishment. The second one is for authentication, digital signatures. So if you want to authenticate that something came from you, you can use your private key to sign it, and then somebody else can take your public key and they can verify that you sent the message, that it wasn't altered, and it authenticates that just like a signature on a letter would do, but in a more electronic or digital fashion. So both those rely on public key cryptography. There are other types. There's symmetric key crypto, but post-quantum is more dealing with the public key cryptography.
Okay, thanks. Another question in the audience is the quantum internet. Again, you hear that a lot. And Denis, you believe in any of the technologies that either you're developing, either on the QKD or the PQC side, how that would relate to the quantum internet?
Oh, absolutely. So there's, again, no standard answer for what the quantum internet is, but if we just go with the premise that it's the transmission of qubits over the internet instead of digital bits, then that'll be what connects the quantum computing infrastructure around the country and the world. So I can connect two quantum computers in two different data centers with a quantum channel and make one big quantum computer. But that same internet could also be used for transmitting crypto keys. Again, it'll be very slow, it'll be very expensive initially, but ultimately that takes away a lot of the security premise that we have to believe is behind the internet, which we know is not true. We know a lot of the data mining, a lot of the harvesting happens over these channels today. All that goes away with a truly quantum internet. There's ways to get around that today without using QKD, but it's a little bit harder and a little bit more expensive.
Okay, great. So let me maybe last questions I'll ask has to deal with how do you guys personally manage your passwords for all the websites you log into? Do you use the same password at each site, or do you have a system? You don't have to tell us the passwords themselves, but maybe you can tell us a little bit about the systems you use to manage your password and keep them secure. And I'll start with you, Dustin. Good
question. I myself use a password manager that generates pretty random passwords and it stores them. And I trust that enough that I feel fine doing it that way. If there's a site or something that I really want to be safe, then I'll probably write it down and stick it in my drawer. But
okay. And how about you, Dennis?
I'm slightly more paranoid coming out of the government community, where any central repository of anything is an easy point of attack, even though they might be perfectly secure. So everything's written down in password books, and I have a different password, long password for every website. And I don't store anything on the computers. I actually have to memorize everything.
You use pencil and paper?
Yeah, it's I can send you one. Here's a password book and
I see.
Crypt logo on.
I actually write down some of my passwords too. Sometimes the old technology works the best. Do you use one of your random number generators to generate the passwords?
Yes, and actually I have a presentation after this. I'm going to make it really easy for the harvesters and hackers. I posted all of my SSN and banking information with our crypto on our presentation. So I gave you the harvesting part. You just have to go out and break it now.
I see. So you get your big bank account.
Yeah. Okay.
We need to wrap up in a couple minutes, but I'll give each of you maybe 2 or 3 minutes, maybe to give just a quick summary. If there's one thing that you would like the members of the audience to walk away with, one idea, what would you want them to remember, let's say a week from now after this conference? And again, Dustin, I'll let you go first.
Okay, thanks, Doug. What I'd want you to remember is that quantum computers will have a lot of great benefits for us. However, in cryptography, they also pose a threat. So I want to make sure you know that there is a threat from quantum computers to the crypto systems that we use today. NIST is in partner with other, the cryptographic community around the world is working on this, and we will very shortly have standards out for algorithms that will protect you. But you need to do some steps on your part to become aware of the threat and to start preparing to transition to these algorithms. So I'd encourage you to look at our NCCOE migration project, and it's got a lot of advice for you. Make sure there's someone in your organization who's tasked to be on top of this, to look at the crypto you're using and to make plans for the future to be crypto agile and keeping up with everything that's going on in this field.
Okay, and Dennis, your final thoughts?
Yeah, so for that same paper that Dustin has done over there, we've done one at the Quantum Economic Development Consortium. It's just getting finished up for the same task, how to prepare, how to be crypto agile. I'll just caution that security is a moving target, and these cyber systems that we're using today will always evolve, and you have to be continuously within that flow, that state of flux, and not stagnant. And quantum is something we've not dealt with before. The threat will come at any time. We just don't know when it'll happen. So the best thing to do is start phasing in these new standardized algorithms that NIST is working on, which everyone is really thankful for, because they're a trusted authority to do that analysis and then to tell us all what to do and when.
Okay, well, thanks. So since I'm the moderator, I can have the last word. So first of all, I want everyone in the audience to understand that this is going to be a big project. As I said earlier, it's going to be tens of billions of devices that are either need to be replaced or upgraded with the new algorithms. And historically, when we've looked at some of these transitions in other encryption systems, it takes about a 10-year period to do that. So, the concern is there's a sort of a famous formula from a researcher in Canada, Michaela Mosca, which says that if you look at the data that you have right now, and it has a long shelf life, could have a shelf life of 10 years, and then you add to it the fact that it's going to take you 10 more years to convert your systems, you could be running into a time when you will have data that's at risk when these very large quantum computers are available. So as the panelists were saying earlier, it really is pretty important to think about this, and you have to time it carefully. You don't want to be premature. You don't want to necessarily jump immediately to an algorithm and then find out that NIST decided not to select that algorithm. But you do want to be prepared, testing out the algorithms, those types of things. But you, at the same time, you also want to think about an attack that some bad guys use called harvest now, decrypt later, that there could be people who are taking your data, which you're sending right now over the lines using RSA encryption, and they're just storing it on a hard drive. And even though they can't break it, they may say, well, we're going to save it for 15 years on a hard drive. And when these large quantum computers are available, we'll buy one, and that could be a problem. Now, that is only an issue for data that is, number one, very important, and number two, has what I would call a long shelf life. So examples I would give, for example, would be health data. The health data for someone, could still be very, very valid 15 years from now, and it could be very important too. So, what I would recommend for the members of the audience is just think about that, read that NCCOE paper that Dustin and Dennis were talking about, and at the same time, put together your plans so that over the next several years, you very step by step implement quantum resistant technologies. And then the final thought I would also say is, at the same time, never believe that if you do that, that you will make yourself safe from all cybersecurity problems. There's lots of cybersecurity problems, things like phishing attacks, physical access to your site, those types of things, which are just as important, and quantum's not going to solve those. So cybersecurity is getting more and more important, and just look at all aspects. Crypto is very important, but look at all the aspects. And with that, I think we have a great session. I thank the panelists, and I'll turn it back to the quantum tech people, and they can move on to the next session. Thank you.
Thank you.